Welcome dear students, welcome to the session. In this session we are going to look into the memory protection. In the previous session we looked into how to do the hardware implementation for the page table. So the paging is the technique that is used to allocate non-contiguous memory allocation, and the paging solves the external segmentation problem. So using paging technique we can solve the external segmentation. That problem is totally solved, and how that is solved is using the paging technique, and how paging technique is implemented using the page tables. Now looking at the hardware, how that page table is implemented. In the previous session we looked the paging table can be can be implemented using a very simplest implementation using a dedicated fast registers. So using a dedicated fast registers we can implement the page table, where we have the PTBR, that is the page table base register, which will contain the address of the base address of the physical memory, and using that technique we can implement page table. There are certain advantages and disadvantages in that particular scheme, and the registers, they work very fast, they work very well, but the amount of the entries that you can have in the table is limited. So if it is around 500 or so records, that is a suitable implementation. The next thing we looked is to solve that problem, to have a bigger entries into the page table. We the next solution, hardware solution that was looked upon, is a small fast lookup hardware cache. Those caches, those are called as a translation lookup aside buffer, TLB. So we looked into the TLB, how TLB can be used to solve the whatever the problem that we encountered in the registers. TLB is it is faster technique, and so we can have a more number of entries in the page table, and in case of a TLB, that particular cache is very fast in accessing the memory. We can have a something called as a TLB hit or TLB miss. TLB hit is like when you find the page number in the TLB entry, then we call it as a hit. The corresponding frame number is retrieved, and the physical address is formed by combining with the offset. If there is a miss, that is called as a TLB miss, we go to another page table, and from there we get that corresponding frame number, and with that we go and access the physical memory. So here whenever we have any miss, that particular entry will be added to the TLB, and when if TLB is relatively free, that entry is done without any problem. If there is any issues, means if TLB is full, the certain operating system, they use the replacement policies, and accordingly it will be replaced. And also we saw with the greater hit ratio. What is a hit ratio? Finding a particular page in the TLB that is having a TLB hit. So that is the hit ratio. If as the hit ratio increases, the memory access time, average memory access time, reduces. Okay. Now next part is the protection, memory protection. So memory protection implemented by associating protection bit with each frame. So there is a new bit is introduced. Memory protection in a paged environment is accomplished by a protection bits associated with each frame. So these whatever these new bits, these bits are kept in the page table. Okay, and one bit can define a page to be whether it's a read write or a read only. So one bit, the possible values we can have is 0 or 1. Accordingly we can define that particular page is a read write or it is just a read only. That is how we can protect the memory. So we can have a particular page which is a read write, both read as well as write, and there could be some pages which is only read. So in those cases the bit will define whether it is a read only or a read write. According to that, operating system can implement the protection mechanism. Suppose if a particular memory is read only, no process is allowed to write on top of that. In any attempt of writing in particular that page where the bit is set as read only, a trap is generated or the memory access violation is generated, and that particular process will be stopped. So every reference to memory or memory access, so whenever we do a memory access, all those memory access goes through the page table to find what is the frame. So far we have seen how it goes to the page table to find the mapping frame number. So every page request, every memory access, okay, whenever we want to access the memory, it goes to the page table to find the frame. At the same time, a protection bit is checked when it is getting the frame. At the same time, we can check the protection bit. If any process tries to write on read only memory, then trap or the memory protection violation is raised. So trap is raised, that is also called as memory protection violation is raised, and such a kind of processes will be stopped immediately. So one additional bit that is stored in the page table to store the valid or invalid bit. So we will have that particular bit is stored as a valid or invalid, either it can 1 or 0, whatever the implementation that operating system will have. Valid, invalid bit attached to each entry in the page table. Valid indicates that the associated page is in the process logical address space and is thus a legal page. So whenever a process is accessing a certain page, and if it finds that the bit as valid, then that particular address space is in the legal address space of that particular process. Let's say if a particular process has generated a address and that particular page entry has the memory protection bit as a invalid, okay, then that process is in a trying to access a space which it is not supposed to. So that is a definite case of a memory protection violation. Okay, if a bit is invalid, then associated page is not in the process logical address space. Okay, some systems provide hardware in the form of a page table length register, page table length register, PTLR. So that indicates the size of the page table. So PTLR, that is the page table length register. Some system provides that register which will have the size of the page table, and this value is checked against every logical address to verify that the address is in the valid range for that process or not. Okay, if there is any failure in this particular test, again it causes a trap to the operating system. Okay, so you can see the diagram here. Valid, that is V, invalid is I, bit in the page table. So this is the page table. So far we have seen here the page table. As we know, this page table is indexed by the page, okay, the page numbers that is generated by the CPU. So this is the logical address that is generated by the CPU, and this particular page table is indexed by the page numbers. So 0 1 2 3 4 5 6 7, so that are this table is indexed by these particular page numbers, and corresponding to each of that index, that is corresponding to each of those page number, we have the mapping frame number. Okay, and using this frame number and the offset. Okay, earlier discussion we have seen what is the offset. Using this frame number plus the page offset, combining those two, frame number plus the page offset, will give us the actual physical address. So for this example, page 0, this page 0 is index, this index is 0. So in the page table it will come to this record with the index 0, and it finds the frame number as a 2, and it will combine with the offset, and this will access this particular page which has a particular frame 2, frame number 2, which has the content of whatever the page. So how it is inside a page, it can be like 4 bytes, 8 bytes, the page size can be anything. Inside this particular frame, frame number 2, we can access each of the byte using the offset, what offset is generated. Now that is how we access. For example, page 3, the 3 index is mapped to frame number 7. Then in the frame number 7 you can see that is the page 3. That is how it is memory access is performed. Along with so far, that is the memory access scheme that we saw so far. In case of a memory protection, each entry, okay, each entry of the page table is having additional 1 bit. Okay, you can see every record here has a 1 bit. Either it will be marked as V or it will be marked as I. Actual implementation can be 1, 0 or anything. So it is marked as V or I, V indicating the valid and I indicating the invalid. So when a process generates the logical addresses, let's say it has the 5 page numbers, okay, 0 to 5, 6 pages, that is indexed here 0 to 5, and these are the logical address space. These are the legal addresses that is generated by the particular process. So all these are the addresses that particular process can legally access. So that's why we have all the states, all the valid, invalid protection bit as set as V. Okay, and beyond that, if this process, particular process, let's say it tries to access any other pages, let's say 6 or 7, if it tries to access those pages, then those are the invalid pages. So there you will get a trap, or the memory protection violation is generated. So this particular process is it is valid to access the pages indexed from 0 to 5, or the frames, the frame numbers 2, 3, 4, 7, 8, 9. Only those particular frames it can access from the main memory. Next is the shared pages. Okay, so shared pages, the advantages of paging is the possibility of sharing common code. So the concept of, earlier we had the contiguous memory allocation for the processes, and contiguous memory allocation had some problems when the processes are getting allocated and releasing those memories. It leaves the holes or the pockets of the memory unused. Even though we have a large number of such holes, we cannot allocate it to any process because it requires a contiguous memory allocation. So it will cause a external fragmentation problem. To solve that external fragmentation problem, we came up with a technique of paging. So in case of a paging, a non-contiguous memory allocation solved the problem of external fragmentation. Now along the paging, one good thing about the paging is it has solved the external fragmentation problem, and along with that it brings the advantages of a possibility of sharing a common code. So if certain processes, they are sharing any common code, so using the paging, we can have a possibility of sharing those common code. Okay, and before we talk in detail about the shared pages, we talk about something we will understand about re-entrant code. So what is a re-entrant code? Re-entrant code, it is the code that will not modify itself, right? So re-entrant code is the code that will not modify itself, that is, it is a non-self modifying code. If it never changes during the execution, so it will never change during the execution, it will remain the same. So that is the re-entrant code. Re-entrant code, you can just think it is a non-self modifying code, so it will not modify itself, and it will never change during the execution. Thus we can have two or more processes can be executed at the same time. So if we have two or more processes can be executed at the same time when we have the same code, same re-entrant code. If the re-entrant code is there, two or more processes can execute it at the same time. But what will happen, each process will have its own copy of registers and data storage, whatever it requires. Every process, it will have its own copy for the process execution. So shared code, one copy of read only re-entrant. So we understood what is the re-entrant code shared among processes. That is, we will talk about this, that is text editors, compilers, Windows system. It can be anything, there could be only one copy, and shared code must appear in the same location in the logical address space of all processes. So shared code must appear in the same location in the logical address space, that is required because it is going to share the pages. Let's take one example. Let's say we have 40 users who want to execute the text editor. So one example is a text editor. There are let's say 40 users, they want to use the text editor, and let's say the code that is used by the text editor, that space would be, the required space for the code would be around 150 kilobytes, 150 kilobytes of code. And on top of that code, we will have additional 50 kilobytes of data for each of the users. So in overall, what happens, we have 40 users and they want to use the text editor. Text editor uses 150 kilobytes of code, that is the space required for the code, and around 50 kilobytes of data. Altogether it would be 200 kilobytes per user. And if you have a total number of users 40, then 40 into 200 kilobytes, 40 into 200, it would be 8000 kilobytes to support 40 users. So we would need 8000 kilobytes of memory space to support 40 users. However, if let's say if the code is re-entrant, okay, if the whatever the 150 kilobytes of code, if it is re-entrant, then what we can do is we can share those 150 kilobyte code among all the processes. So in turn, what would happen is, if we share that 150 kilobyte of a memory, then we would need only one copy of that particular memory. So only one copy is required for the re-entrant code. So 150 kilobytes. Then what remains? every process or the user require 50 MB of the data, and 50 kilobytes of a data. That data is different for the users, all the users, 40 users. So we need to have that 50 kilobytes of a data, because every text editor, the users what they are entering in those text editor, the data would be different. So 50 kilobytes of data for 40 users is different, but the code, the text editor code, that is 150 kb is same for everybody, so that can be shared. So we will share 150 kb, and then plus we need 50 kilobytes for every user into 40, that is 40 into 50 is, we get it as a 2000 kilobytes, plus additional 150 kb for the code which is shared by everybody. So overall we would require 2150 kb of data. So now you can see that without using the shared pages, we would have used around 8000 kilobytes. With the use of the shared pages, we reduce the memory requirement to 2150 kilobytes. If you remember the there was in the process communication, interprocess IPC, in the interprocess communication, one of the method we talked about is the shared memory. So if you remember, there were different methods how IPC, interprocess communication, was implemented. One of the method was the shared memory. Okay, and that shared memory method is implemented using the shared pages. So this is how you will understand how that shared memory method of interprocess communication is implemented. It is implemented using the shared pages technique. So in the next page, so this is the shared page example. We will have next, this is the same diagram. I will show it in the next page, which is from the textbook. Okay, this is from the textbook. We have, you can see here, process P1. So these are the example of the processes that are running a common re-entrant code. Let's say, for example, what we talked about is a text editor, and text editor we talked 150 kb of a code that is common for all the process. So here also we have ed1, ed2, ed3, that is the common. These are the three pages which is common for all the processes. We have process P1, process P2, process P3, and these are the page tables corresponding to the process P1. This is the page table of P1, this is the page table of P2, and this is the page table of P3. So in this particular scenario, if we didn't had a shared pages implementation, what would have happened is every process we had ed1, ed2, ed3 and data 1. So whatever the memory allocation it is here, so in the physical memory we would have had ed1, ed2, ed3 and data 1. Similarly for the process 2, we have ed1, ed2, ed3 and data 2. So different set of a data. Again in the physical memory we would have had ed1, ed2, ed3 and data 2. Similarly for the process 3, ed1, ed2, ed3 and data 3. So we would have been having this particular pages which represents the code duplicating 3 times. Okay, even though this is a re-entrant code that can be shared by many processes, if non-shared pages implementation is done, then those pages will be duplicated. In case of a shared pages, what we will do is the ed1, ed2, ed3 will be shared by all these 3 processes, and it will have a separate memory allocation for data 1, which is the data of process 1, data 2, which is the process of data of process P2, and data 3, which is the data of process P3. So if you can see here, the ed1, there is a one copy of ed1, ed2 and ed3, that is at the frame number 3, 4 and 6. So in the page table of all the three process, you can see the first three mapping of so this is the page, this page is page table is indexed with the page number. The first three location is 3, 4, 6 corresponding to this ED1, ED2 and ED3. So 3, 4, 6 and 3, 4, 2, and there would be separate allocation for the data 1, that is 1, and this is 7, data 2 is at 7, frame number 7, and data 3 is at frame number 2. So this is how we can share the reentrant code, and we can reduce the memory requirement using the shared pages. Okay, next is the structure of the page table. Okay, in this we explore most common techniques of structuring the page table, how the page tables can be structured. So there are three different ways of structuring the page table. One is a hierarchical paging, hashed page tables, and inverted page tables. So we will look into these three individually: hierarchical paging, hashed page tables, and inverted page tables. So hierarchical pages, okay, hierarchical paging in modern system supports logical addresses, very large sizes of the memory it supports. The address space can range from, let's say, 2 raised to 12 to 2 raised to 64. Okay, in such environment where there is a large logical address space, we use the hierarchical paging technique. Okay, let's say we have a 32-bit logical address space. Okay, so here break up the logical address space into multiple page tables. So that is the technique here we used. We will discuss how this is done. A simple technique is a two-level page table. So let's take an example. Let me see if that example is given. Okay, so here the technique here is the logical address is broken into multiple page tables. So whatever the logical address space, we break up into multiple page tables. That is the technique that is used. And first of the technique, simple technique, is a two-level page table. So we will have a two-level page tables. We will understand how that two-level paging is done. A logical address on a 32-bit machine with a 4K page size is divided into, okay, a page number consisting of 20 bits and a page offset of 12 bits. Okay, so we have a 32-bit logical address space, and the page size, each page size is 4 kilobytes. So 4 kilobytes is how much? It is 2 raised to 12. So how many pages we would require? The number of how many page entries we would require? That would be 2 raised to 32. So what is the total address, the memory that is available? 2 raised to 32 divided by size of a page. And what is the size of the page? Size of the page is 4 kilobytes or 2 raised to 12. That means 2 raised to 32 divided by 2 raised to 12. So those are the number of entries. So how much is 2 raised to 32 divided by 2 raised to 12? That is nothing but 2 raised to 20. So 2 raised to 20 is the number of entries that would be present in the page table. So the page number consisting of 20 bits. So 2 raised to 20. So 20 bits will be required. And how much is the page offset? Page offset is what? Page offset is the once 2 raised to 20 is the number of pages. So those many pages we can have, and inside one page we have a memory of 4 kilobytes, that is 2 raised to 12. So each byte is addressed with a 1 bit. So that is 2 raised to 12. So assuming each entry is 4 bytes, here the total requirement, so total requirement would be 2 raised to 20 is, you can say, about more than 1 million. Okay, it comes as more than 1 million, and we have 4 kilo. Okay, 4 kilo, 4 into 1 million, it will come around 4 MB. So 4 MB is the memory requirement for the particular process. Okay, since the page table is the page number is further divided into now we have this as a page number is consisting of 20 bits. In two level, what we do is, we understood how we got this 20 and 12 bits. Now in a two level paging, so instead of having 2 raised to 20 and those many pages, what we can do is we can divide this page number. So when we divide this page number, we will have a 10 bit page number, that is P1, and another 10 bit page offset, so we will have a P2 here. Since the page table is paged, the page number is further divided. Now we can see here the main page table is paged, the main table itself is paged. So what is the meaning of that is, we will have a page inside another page. Okay, page inside another page. If you just think of a your regular book, so there are so many pages are there, and what we are doing is inside one page we are going to have let's say that page is divided into another smaller chunks. Okay, so that particular page, let's say you have a page number 200. Okay, up to 200 you have a book of 200 pages, and inside each page, let's say you have divided that into 8 sections and you named it as ABCD. So we have a page A inside a page, so that gives a page inside another page. How we access the outer pages? Using a 10 bit page range. So using a 10 bit we will access the outside page, and when we hit particular page, we have another 10 bits for the page inside the page. So I will show you the next diagram, it would be more easy to understand. So the logical address, we have this page number. Since we have two level paging, this page is divided into pages again. So we have pages inside the page. So we have outer page of P1 which is indexed by 10 bits, and using this index we can access the P2. So there is a page inside this page. So here you can see where Pi or the P1 is the index into outer page table, and P2 is the displacement within the page of the outer page. So I will show you the, then this is the regular offset, so there is no change with the offset, only this part, this 20 bits is divided into outer page, and then we will have a offset there. Okay, so you can see here this is the outer page. Okay, this is the outer page, and this outer page is indexed. Okay, is indexed by this. So you can just think this outer page is partitioned. Okay, and each partition has a one more page inside. So this complete table itself is a page. Okay, outer page, this itself is a outer page, and this is divided into many pages, and we have each block. Okay, this whole page is divided into many pages, and in each of the section we will have a one page, and in that page we will have a reference to the frame number. So this is how it is a two level. So we have a outer level page, and there is a page inside this page. So this is the page, and these are the pages that are, these are the different pages that are available in this bigger page. So we have a one bigger page, inside that many smaller pages. So this is the smaller pages. Okay, or you can say offset. inside this bigger page. How the address translation is done? Address translation scheme for a 2-bit level 32 bit paging. So in case of this address translation, we have a logical address. Now the logical address, we have P1, P2 and D. So if you go back here, we have page number, then offset inside this page, and then we have the page offset. Okay, so earlier scheme is what, we used to get the page number and the offset. So this page number will corresponds to the frame number, and frame number plus offset will give the physical address. Now we have this page number divided into 2 levels. First we have one level with this example is a 32 bit, 10 bit plus 12 bit, so total is 32. So this is the outer page. Okay, so this is the outer page. Using those 10 bits, we will access the section. Okay, what section of the page you want to access. So that is the P1, and once you get into that particular section, what different page inside this section. So in this section there are different pages. In this section, what page you want to access is given by the P2. So outer page table is this one, which is indexed by P1, and inside that you index it by the P2. That's the page of page table, and there you will get the frame number. So you will get the frame number corresponding to P1 and P2. There you get the frame number. That frame number plus offset will give the access to the physical memory. That is how the address translation is performed. Hashed page table. So this is another technique of structuring the page table. Here the hashed page tables are used when the address space is more than 32 bits. So if the address space is more than 32 bits, a hashed page table is used. Here we have a virtual page number is hashed into page table, and this page table contains a chain of elements hashing to the same location. So we have a virtual page number which is hashed into a page table. So the virtual page number is hashed inside the page table, and this page table contains a chain of elements hashing to the same location. It will hash to the same location. Virtual page numbers are compared in this chain searching for a match. Okay, so this chain searching that is done using a linked list. Okay, if a match is found, so we will look for that particular page number. If a match is found, corresponding frame, physical frame is extracted. Corresponding physical frame is extracted, and using that frame and the offset, we get the address of the physical memory. So in the next diagram we will come to understand what is the hashed page table. So this is the scheme here. We have a logical address P and D, and this is the hash table and we have the hash function. So using this page number, we search into the linked list. Excuse me. We search into the linked list and we look for that particular page number. When we look for that particular page number, and if it is not present, okay, if it is present, the S, Q is the page number, if it is present, S is the frame number. Okay, and if it is not present, the third element, so there would be 3 elements in the hashed table. The 3 different elements that are in the hash table is, the first one is the virtual page number. So this would be the virtual page number, and second would be the value of the mapped frame. So this is the frame, this is a virtual page number, and this is the frame number. And next one, the third one is, the third field is the a pointer to the next element in the linked list. So it will have a pointer to the next element in the linked list. So I will search for P here. If I don't find it, I will go to the next element, okay, in the linked list. So I will check here. Now P, we have the match. So this P is exactly same as this virtual page number. Then this is the frame number that is returned, and that frame number plus the offset will make the physical address. So that is how the hash tables are used.